Assalamualaikum warahmatullah and hello everyone. In this video, we're going to learn about a new topic called electrochemistry. Before we go in depth learning this topic, you need to first understand what does the name of this topic referring to. Electrochemistry is about the relationship between chemical reactions and electricity. When we're studying electrochemistry, there are basically two main ways that chemical reactions and electricity interact. The first way that shows their interaction is when certain chemical reactions can create electricity, where we would use the setup of a voltaic cell. While the second way is vice versa, where electricity can make certain chemical reactions happen. These interactions requires us to set up an electrolytic cell. We will look on an example of both situations throughout this topic. But for today's video, we will be discussing only on voltaic cell, also known as galvanic cell. Voltaic cell is an electrochemical cell that uses spontaneous chemical reactions, both oxidations and reduction, to generate electricity. Before we jump to the core of this topic, there are a few things need to be sorted in order to understand this cell better. First, you need to know how to differentiate between both electrodes and cell potential. Cell potentials can be determined by using voltaic cell. We'll be discussing on its components, operations, and calculations of cell potential. Next, we will discuss more on standard hydrogen electrode (SHE), where electrode potentials can be obtained. With all the examples discussed in voltaic cell and SHE, we're going to relate it to the standard reduction potential or SRP table. Last but not least, we're going to use Nernst equations to calculate cell potential at non-standard conditions. We got to be familiar with these two terms, electrode potential and cell potential, because we're going to use them quite frequently throughout this subtopic. When we have an electrode deep in an electrolyte, the electrode will lose or gain electrons depending on its nature. Let's say the electrode is zinc and it loses electrons. The potential developed between an electrode and electrolyte is known as electrode potential. So, for an individual half cell, we will get electrode potential. It is impossible to determine electrode potential by depending on only one half cell, as there must be two half cells in a cell. Therefore, electrode potential is determined by pairing up with standard hydrogen electrode (SHE). For a combination of two half cells, where one electrode loses electrons while the other electrode gains electrons, the potential developed by these two cells is known as cell potential. Cell potentials can be determined by using voltaic cell. This is the basic setup of a voltaic cell. It starts with two beakers containing electrolytes. For this setup, we use zinc 2+ aqueous and Cu2+ aqueous. Then, we dissolve a piece of metal in respective electrolytes. For this example, we're going to use zinc solid and copper solid. Next, we will use wire to connect both electrodes. When we do this, something amazing is happening. Electron starts moving through this wire, indicating there's electricity. We can take a voltmeter and hook it up to this wire, and the voltmeter can give a reading of potential difference. There's one more important part of voltaic cell called a salt bridge that connects these two solutions. Salt bridge is used to maintain the neutrality of solutions, which we'll talk more later on. Now, let's try to understand what causing electrons to move through this wire and create electricity. Here is the magnifications of the different parts of the voltaic cell. As you can see here, zinc solid comes from the electrodes on the left side, while zinc 2+ aqueous comes from the solutions on the left-hand side. Same goes to the next beaker where we have copper solid and copper 2+ aqueous. We said earlier, when we hook everything together, electrons starts flowing through this wire. When this happens, we kind of start a tug-of-war between the zinc and the copper. They are fighting for the electrons, one of them wins and one of them loses. Based on the oxidations reductions reactions we have discussed earlier, we know that copper has stronger pull for electrons. Therefore, copper will win, while zinc, who has weaker pull for electrons, will lose in the war. What will happen here is zinc will give away 2 electrons, and these electrons enter the wire and move towards the copper. When zinc do that, it causes its charge to change from neutral atoms of zinc solid to a metal ion of zinc 2+. This change has a big effect on the atom as zinc 2+ is no longer part of the solid metal anymore. It floats off and dissolves into the solution, which eventually reduces the size of zinc electrode. So that's what happened to the zinc. Those electrons who were given away by zinc will make their way down the wire to the copper. Then, one of the Cu2+ from the electrolyte who has stronger pull for electrons will pick up those 2 electrons. Gaining these 2 electrons is going to get rid of that 2+ charge. This change will lead to the formations of neutral atom of copper, as Cu2+ has now become part of the solid metal, which later will cause an increase in copper electrode size. So that is where this electron movement through the wire coming from. When voltaic cell begins to run, zinc atom will keep losing electrons and zinc 2+ will keep entering the solutions. While for Cu2+, they will keep gaining electrons and turns into neutrally charged copper atoms and attach to the metal. After just a little while, we could see positive charge begins to build up at the first half cell, and for the second half cell, we could see we have less positive charge in the solution, means negative charge begins to build up on this side. If the positive and negative charge build up too much, the cell will stop running. So that is where the salt bridge comes in. Salt bridge is a tube shaped like upside down U that is filled with salt. Let's say we use KCl solutions. At the end of the bridge, we've got a cotton plug that prevents the solutions from just pouring out into the half cell. Although there are some barriers made, those ions from the salt bridge are able to slowly pass through the cotton plugs. So, for the side with positive charge building up, the negatively charged Cl will move over into the half cell and to help balance out the charge. Same goes with the side with negative charge building up, the positively charged K will move over into the half cell and to help balance out the charge. So, this is how the overall reaction will look like. Zinc solid releases 2 electrons and zinc 2+ enter the solutions, resulting smaller size of zinc electrode. Copper 2+ pick up the electrons and moves to the metal, resulting bigger size of copper electrode. Hence, cell potential of positive 1.10 volt is obtained. We know that zinc will undergo oxidations and copper will undergo reductions. Now, we will put these 2 half-cell reactions together to get a net ionic equation which shows the overall oxidations reduction reactions via eliminations of electrons. When we are talking about voltaic cell, we are often represent them in the shorthand abbreviations of chemical reactions called cell notations. Cell notations is a way we can show what's going on without drawing a cell diagram. We are going to have these notations written from anode to cathode. We'll start with zinc releases 2 electrons, where zinc 2+ being released to the solutions. We will use one vertical line to present every change happened in the state of matter. From oxidations, we need a salt bridge to get to the reductions. Salt bridge is represented by 2 vertical lines. After crossing the salt bridge, we'll put informations regarding reductions process. We start with Cu2+ aqueous, and since reductions process ends with Cu solid, then we need to put one vertical line before Cu copper solid. From the voltaic cell we have discussed earlier, we gonna look at how each zinc and copper electrode potential is obtained by using standard hydrogen electrode. Standard hydrogen electrode is a half cell that is prepared using inert electrodes such as platinum or palladium under standard conditions. Those standard conditions are 1 molar aqueous solutions of strong acid, 1 atm of hydrogen gas, and temperature of 298 Kelvin or 25 degrees Celsius. Electrode potential of hydrogens is 0.00 volt. On the left, we have a zinc half cell which composed of a zinc electrode in a 1 mol per liter solutions of zinc 2+ ion. The zinc half cell is connected by a wire and a salt bridge to the standard hydrogen electrode on the right with electrode potential of 0.00 volt. Zinc will give away 2 electrons, and these electrons enter the wire and move towards the platinum. Size of zinc electrode is seen to decrease after a while. Hydrogen ions from acid solution in SHE will take the electrons to form hydrogen gas, hence bubble of gas released. Positive charge building up in the left beaker will be neutralized by the negatively charged Cl from the salt bridge. Same goes with the beaker containing SHE where negative charge building up, the positively charged K will move over into the half cell and to help balance out the charge. From these reactions, we know that the electrode potential of hydrogen is positive 0.00 volt, and voltmeter is seen to give a reading of positive 0.76 volt, which is the standard cell potential inert cell. To find electrode potential of zinc, we need to first identify who's going to be the anode and the cathode. How do we know who's going to be one of those? Based on the observations at each electrode. Since bubble of gas released at SHE, therefore it will undergo reductions which take place at the cathode, while size of zinc is reduced, indicating oxidation process which takes place at anode. We will use the formula of standard cell potential to determine the electrode potential of zinc. The general formula begins with standard cell potential inert cell equal to electrode potential of a cathode minus electrode potential of an anode. Simply substitute the value. Finally, we're going to get the electrode potential of zinc, which is negative 0.76 volt. This value is one of the elements that made up the standard reduction potential SRP table. Zinc will undergo oxidations and hydrogen will undergo reductions. Now we will put these two half cell reactions together to get a net ionic equations. We start with zinc solid followed by one vertical line, then zinc 2+ aqueous. If there's concentrations provided, we need to include those values in the cell notations. And for this case, we have 1 molar of solutions. Next, we have salt bridge, which will be represented by using 2 vertical lines. Reductions process taking place here starts with 1 molar of hydrogen aqueous, followed by 1 vertical line and hydrogen gas of 1 atm. Every cell notations must have an electrode at the end. We use platinum for standard hydrogen electrode. Therefore, one final vertical line is placed before platinum solid. For SHE paired up with copper, concentrations of H+ at hydrogen electrode increases as hydrogen gas undergo oxidations at the anode, while copper electrode is seen to become thicker as reductions reaction is taking place at the cathode. Positive charge building up in the left beaker will be neutralized by the negatively charged Cl from the salt bridge. Same goes with the beaker containing copper electrode where negative charge building up, the positively charged K will move over into the half cell and to help balance out the charge. From these reactions, we know that electrode potential of hydrogen is positive 0.00 volt and voltmeter is seen to give a reading of positive 0.34 volt. Now, we are going to find the electrode potential of copper. The same formula as in zinc, will be used to determine the electrode potential of copper. Simply substitute the value into the formula. Finally, we're going to get the electrode potentials of copper, which is positive 0.34 volt. This value is one of the elements that made up the standard reduction potential SRP table. Determinations of electrode potential, for example zinc and copper at standard condition, has resulted in a table of standard reduction potential or SRP. SRP table consists of half reaction that is written as a reduction. As we can see, this table provides two range of readings. Elements located higher up on the table have more positive values compared to those lower down the table with more negative values, leaving only hydrogen electrode with 0.00 volt as reference. Why these values are listed this way? This is a reduction table. Recall that reduction means accepting electrons. Logically, if they initially have less electrons, they are most likely to have a more positive value. Hence, reduction is favored. When more electrons are present, elements will have more negative value. Hence, oxidation is favored. Let's check if our assignment on anode and cathode based on observations from previous example are true. Zinc has SRP value of negative 0.76 volt, whereas copper has SRP value of positive 0.34 volt. Well done! They are all correct. Just to remind you once again, since we are dealing with movement of electrons via spontaneous chemical reactions that happen on its own to create electricity, the first half cell which will initiate the reaction must have so much electron to start with, i.e., more electrons represented by more negative value means negative terminal. On the other hand, the second half cell that completed the reactions must have less electron on it, i.e., less electron represented by more positive value means positive terminal. To determine electrode and cell potential, always choose metal with more negative value to become the anode, while more positive value to become the cathode. Therefore, it can be concluded that anode undergo oxidations and have negative terminal, which in this case zinc. Cathode undergo reductions and have positive terminal, which in this case copper. Our previous example on voltage cell often addresses the calculations of standard cell potential and electrode potential, where E naught cell is equal to E naught cathode minus E naught anode. So, we are talking about standard conditions for both situations, where concentrations of solutions are 1 molar and temperature of 25 degrees Celsius. What if we are given different concentrations of solution? Can we still use these equations? For different concentrations, we can use Nernst equations to calculate cell potential E cell. Cell potential is equal to standard cell potential minus RT over NF ln concentrations product to the power of X divided by concentrations reactant to the power of Y. The X and Y value can be determined from the coefficients of overall redox reaction as well as N, which is the number of mole of electron. R is gas constant of 8.314 J per K per mole, T is temperature in Kelvin, and F is a Faraday constant of 96,500 Coulomb. But these equations can be standardized to the following equations if the temperature is set to 25 degrees Celsius or 298 Kelvin. Cell potential is equal to standard cell potential minus 0.0592 over N log Q. Q is a reaction quotient. It can be either concentrations or pressure or both based on the net ionic equations. N is the number of mole where we get from the overall redox reactions. So, it is very important to first find the net ionic equations before using these equations. At equilibrium, we know that E cell is equal to 0. Therefore, E naught cell is equal to 0.0592 over n log K, where K is the equilibrium constant. That's all for today's lecture. Thank you for listening. Don't forget to attempt the formative assessments before this hour end to secure your attendance in this lecture. Goodbye.